Okay, this is still Chapter 4, Section 1. This is on arc length and linear and angular speed. These are some of the objectives that we're going to be doing here. This is a concept that uses what we've been learning in trigonometry. It uses circular functions, which of course is what we're dealing with trig, but it's also dealing with some real-life application, and so we want to talk about that. We're going to do some exercises in class, but be sure and take notes on this in your composition notebook. Copy down the examples, anything especially that it says in the presentation to copy down. And there will be a question for you to answer at the end. Okay, arc length. If you go back to geometry, we remember that the circumference is the distance around, completely around a circle. And so we know that the circumference, I need to hit that button. There we go. The circumference of a circle is 2 times pi times r, and that would be all the way around. And we know that r, of course, is the radius of the circle. And so arc length then would just be a piece of the circumference. It's just part of the circumference. And this red part right here on this diagram is the arc length. And we denote that with an S. Now, I'm not sure why it's an S. Probably because the A, the R, and the C already refer to things in geometry, and so they just wanted to make it a little more clear. Okay, we also know that this angle right here is a central angle, and it's a central angle because its vertex is on the center of the circle, and we refer to that angle as theta. And you'll notice that all the way around a circle, the angles in degrees, remember, would be 360 degrees. In radians, we know that that's 2 pi. So all the way around, all the angle in the entire circle would be either 360 degrees or 2 pi radians. Now to find the arc length, on the arc length, what we're looking for is a part of the circumference, and it's actually a ratio. It is like a proportion, so a ratio. So if we could set up the ratio of arc length to circumference, which is 2 pi r, we could set that equal to the ratio of the central angle to all of the angles in the circle. And since we're using radians now in trig, we're making the conversion from degrees to radians. Instead of putting 360 degrees, I would put 2 pi r. Well, to derive a formula for arc length, what I want it to look like is S equals. So I'm going to cross multiply both sides, use my algebra skills. Oh, and I've made a mistake here. Let me take this off. This is not 2 pi r. That's just 2 pi. That's just 2 pi. Because we're talking about radians here. Radians over radians, and then this would be arc length over circumference. Sorry about that. Alright, so now to solve for S, multiplying both sides by 2 pi, and then multiplying both sides by 2 pi r, gets me 2 pi r theta. Solving for S, I'm going to divide both sides by 2 pi, and I end up with S equals r theta, which is what I have here. Remembering that r is the radius of the circle, and S is the arc length. Okay. So here are some story problems that we're going to work. They are not particularly interesting, but they do kind of demonstrate how this works and the relationship between the pieces of the formula and the concept of linear and angular velocity. So what we're looking at, anytime we talk about speed or velocity, we're talking about a rate, like feet per second or centimeters per minute, a rate. Linear velocity, you know, like an actual moving miles per hour, blah, blah, blah. Okay, so right here, if we have a clock, and we're going to talk about a circular clock and not a digital clock because that doesn't really fit what we're talking about here. It says it has a minute hand that's 16 centimeters long, and how far does the tip of the hand move during 15 centimeters? So it's asking us how far does the tip of the hand move? Well, what does that indicate? What are we looking for? Well, we are looking for this moving from one distance to another, and on our circle that is arc length, which is S. The minute hand is 16 centimeters long. That's going to be my radius. And then it's moving during 15 minutes. Well, if you remember on a clock, this is 15 minutes here. So in radians, that would be theta. 15 minutes is not radians. So we look on this picture and we think about the unit circle. And if we think about this being 0 degrees right here, and this would then be what? In radians. Now some of you have said, well, that's a right angle, so that's 90 degrees. But once again, I did not say degrees, right? That would be 90 degrees. I said radians. So radians would be pi over 2. All right, so I think about the relationship. The arc length is equal to the length of the radius times the angle. And then this becomes a fairly simple problem. So S is going to be equal to 16 times pi over 2, or 8 pi. Now, 8 pi is how far? How far is what we want to know. Do you know how far 8 pi is? I don't. So this is at the point where you would convert it from an exact answer, this is exact, to an approximate in decimal. And the approximate in decimal is 8 times 3.14, which is approximately, and this is in centimeters. So that's how far it travels. All right, so the same thing with these two. And so what I'd like for you to do is stop the video, work these in your notebook, and then come back and I will work through the solutions. Okay? Alright, so here we are back again. In the circle with a 12 meteor radius, these were not particularly interesting problems again. You still start with S equals R theta. The central angle is 2.6, so I have is S equals 12 times 2.6, which you should have got, you should have figured it to be 31.2 meters. Okay, same deal here, not a particularly interesting question. You probably got it done very quickly. The circle has a radius of 35. I did this. The circle has a radius of 35. So it's looking for theta times 35 equals 20. And so I end up with approximately 0.57 radians. Okay, because I am looking at what is the length of that. Okay, so let's talk a little bit about angular and linear speed. These diagrams kind of give us a good indication of what's going on here, and I did several of them just hoping that someone would understand them. Angular speed is how fast the angle is changing. So this angle, by the angle I'm talking about the central angle. So what we've done here is instead of just having a set length, we are saying that this is actually moving around the circle. A particle is either moving in a circular motion around the circumference of the circle, or the angle is changing as it moves around the circle. So these are generally circular paths, and what we're looking at is a rate. So minutes per second, miles per hour, feet per second, da-da-da. Angular speed is going to be measured in like radians per second, or in revolutions per second. So how far is it going around the circle? So when you're talking about different types of speed, you're talking about how fast that angle is changing. And you can see on this diagram over here that we have the angular speed is showing going around the circle, linear speed is going out, and this is the radius of the circle. And this is just, this one down here is just another way of saying that this is the change in S. This is the Greek letter delta. So the change in S and the change in theta. And so in order to find linear speed is usually referred to with a V. Angular speed is with a W, usually in italicized. They look italicized. And so I want you to copy this, stop the video, copy at least one of these diagrams in your composition notebook and the definition. And then we're going to work with these rates. So a lot of these things are using unit conversions. If you've had any chemistry courses, you probably have done unit conversions before. All right, so you can actually derive a formula which relates to the two velocities. In other words, you can put both things together. So we're going to start with the definition of linear velocity. And linear velocity v is the arc length, that's s, right, over time. Or in other words, this is how fast it's changing. So the distance per time. Okay. Now, if you'll recall the arc length formula, s equals r theta, then you can actually substitute r theta in for s. So I have v equals r theta over time. Okay. So if you'll recall, then, that angular velocity is the change in theta over time, then you can see that if you rewrite this just slightly, you can substitute angular velocity for linear velocity, and you have this formula. And this is a combination of them both. So this is linear velocity, and this is angular velocity, and this is the radius. Okay, so here is an example of where we're going to find both angular and linear velocity or speed in an example. All right, so we have a wind turbine. We have these in Oklahoma. Those are the ones that generate electricity, and they have blades that are 116 feet long. And the propeller rotates at 15 revolutions per minute. Okay, so anytime we're given a problem, we want to think about what do we know? What do we know? What is given? All right, so the first part here is we're going to look at the given. And I'd like you to stop the video at this point and write down what you think the given is in this problem. Okay, so the radius, I'm sure you wrote, was 116 feet. And the linear speed is 15 revolutions per minute. Right? So it is rotating at 15 revolutions per minute. Revolutions is a linear velocity. Okay, so this is linear speed. Okay, so the second thing we want to look at is what is the measure of the central angle after 1 minute? Okay, so we know that the propeller rotates at 15 revolutions per minute. All right, so I want to know what the angle is. I know that it's rotating at 15 revolutions per minute. How much is one revolution? Well, in one revolution, how far does the angle travel? How does the angle change? And we're in radians, right? We're still in radians. So you would probably tell me 360 degrees, which is absolutely correct. It's going to go 360 degrees in one revolution. But we're doing that in radians, which is 2 pi. So we end up that theta, the central angle after 1 minute, is going to be 30 pi radians. Because we're talking about an angle, it has to be in radians. Okay, so let's look at angular speed. Well, we know that angular speed is the change in the angle as it goes around the circle, right? So the change in theta over time. So angular speed is the change in theta over time. Well, our time is in minutes. Our angular speed is going to be the angle that it is in one revolution, and so this is going to be 30 pi radians in a minute. So this is 30 pi radians per minute, and that's angular speed. So that's how fast the angle is traveling, or the angle is changing as the wind turbine is spinning. All right. Then the last thing we want to look at is linear speed, and we're looking at how fast the turbine speed goes around. Well, we have several formulas for that. One of them was, the arc length per time. Right, we had V equals arc length over time. Well, we don't have the arc length here anywhere. So why don't we use something in terms of angular speed? Well, we do know that. So V is equal to the length of the radius times the angular speed, and we already have that. So this is going to be, the linear speed is going to be the radius, which is 116 feet, times the angular speed, which is 30 pi radians per minute. This is not an angle, this is distance, so we don't use the radians, and we're going to say that the linear velocity is 10,933 feet per minute. Okay? Okay, so here is the summary of some of the formulas that we've talked about, and they're all together here. And I'd like you to copy these down in your composition notebook so that you will have them all in one spot. And then you can stop this and then write it down and then come. Okay, so then the last thing I want you to do, here's an interesting problem that I want you to think about. I want to know what your thoughts might be. I'm going to go through some things here, and then I would like for you to answer the question that I have after this one. And it says, if the arc length of a circle is 4 centimeters and the radius of the circular path is 5 centimeters, then theta would be what? Okay, so whenever you're given kind of an open-ended problem like this, the first thing to do is to go and think, what do I know that has theta, arc length, and possibly radius in it? And we're back to our original thing where we said the arc length was equal to the radius times the central angle in radians, right? But that is not theta equals. So some of you have already seen that if I just divide both sides by r, then I know that theta is going to be the arc length over r. Okay, then it's just a matter of plug and chudge. I get this. And so this is like 4 to 5. Now what does this mean? What does this mean? Because this is a ratio, is it not? Arc length to radius. It's a fraction, right? Arc length to radius. So in terms of the angle, the central angle is equal to the arc length divided by the radius, or the ratio of the arc length to the radius. So to write this out at work, you would say at the central angle, theta, the arc is 4/5 of the radius. And some of you are going, wait a minute, that does not directly follow. This is at theta, the arc is 4/5 of the radius. How is that true? Well, let's think about this a minute. If I have the arc is 4/5 the radius. So what they're saying is this, right? Isn't that what this says? The central angle is 4/5 of the radius. Okay, so here's what I want to know then. I want you to, hang on. I want you to go, sorry about that, I got a phone call. I want you to go to the next screen and write a sentence that explains these two examples in your composition notebook. Copy down the question, and then explain in words what these mean, and try to come up with as many relationships as you possibly can for these. Don't ask anybody, just write them down. We're brainstorming. If they're correct, fine. If they're not correct, we'll talk about that tomorrow in class. But I want you to understand not just the formula, but the concept behind it. Another thing that I thought might be kind of interesting, if I can add, is to talk about the definition of pi, and as it relates to circumference. So I want you to think about that before tomorrow, and be sure you get all of that in your composition notebook. I'm going to be checking those most likely first thing, and I'll see you in class.